Okay, for those of you who are good with the top half, which was simplifying answers from applying the quadratic formula, we're going to move on to the second half, which is how to use the discriminant and the quadratic formula to actually solve quadratics, both easy and more challenging. So first, the discriminant is part of the quadratic formula. It is the part that is under the square root. It is b squared minus 4ac, which is this part right here. Keep in mind, you should have parentheses around b before you square it. That will prevent a lot of sign errors that tend to occur. For example, if b happens to be a negative value. So, when you use the quadratic formula, it is actually derived from taking this quadratic, ax squared plus bx plus c, and doing this process of completing the square, and that's where the quadratic formula came from. It was not just randomly made up by some genius. It was from observing patterns that they saw when they solved quadratics. So they took it a step further and turned those patterns into a formula that you now use. So that's what should go in this box. I am not going to take the time to do that on this video. However, I will put it on a third video, which is separate. So what I'm going to do right now is I'm going to go down to the bottom half of the paper, that bottom quarter of the paper. So from the quadratic formula, part of that is the discriminant. So the discriminant, again, is the part that's under the square root. So it is the b squared minus 4ac. That eventually, after you simplify that down to a single number, then you take the square root of. So what that b squared minus 4ac tells us is, first of all, it tells us the number of solutions and whether they're real or non-real. And it'll also tell you whether or not you were able to factor the original quadratic as opposed to having to continue with the quadratic formula. So first of all, when you evaluate b squared minus 4ac, and we'll do examples of this on the back, if you do get a perfect square, for example, if we go up to number 1, where the number under the square root is a perfect square, 25, what that tells us is that we could have solved the original quadratic that resulted in that answer by factoring. If we get something that's not a perfect square, like any of the other 3 examples in the warm-up, what that tells us is that we would not be able to solve the quadratics that resulted in these answers by factoring. Instead, we would have to use the quadratic formula, which if you already have the discriminant, you might as well just finish it, or you could have completed the square to solve it and then solve directly. So that's one thing. One thing is it tells us if it is a perfect square, then the quadratic is factorable. Second thing is it tells us the number of solutions and whether they are real or not real. So when we say 0 real solutions, I actually want you to instead think of that as, what that means is there are 2 complex or imaginary. We'll say imaginary. Every solution is complex. When it involves taking the square root of a negative number, which is what this is saying, is that the number under the square root is less than 0 or negative, that means that we have no real solutions, but we have two imaginary solutions. When the discriminant is 0, we have what looks like one real solution, but remember that actually has a multiplicity of 2 because it was solving a quadratic, so if there's only one solution, that means it's used twice because every quadratic has 2 solutions. So the way we write that, remember, is m:2, which means it has a multiplicity of 2, or it's used twice. All right, let's go to the back and start using this so you can see it in action. All right, so we have 3 parts to this, just like we have 3 parts on the homework. Part A is to actually find the discriminant. Part B is to say the number of solutions and type. Type meaning real or imaginary. And part C is what methods can you use to solve the following. So if there's more than one method you can use, then you are supposed to list all of them. Okay, so let's take a look at number 5. First thing I want you to do is always check the discriminant. So since I had the discriminant on the front circled in this light blue, remember the discriminant is the part of the quadratic formula that's under the square root, so b squared minus 4ac. Remember those values come from having your quadratic in ax squared plus bx plus c equal to 0 form, and then your coefficients are going to tell you your a, b, and c values. A is always the coefficient of x squared, b is always the coefficient of x, and c is always the coefficient of the 0-powered x, or the constant. All right, so then with number 5, first thing we want to do is identify our a, b, and c. A is 1, b is -7. The sign in front of a number always goes with it, and c is 12. So from there, we can plug that right into our discriminant. So we would have discriminant is b, which is -7 squared minus 4ac. That would be 49 minus 48, which is 1. Now, 1 is unique. 1 is a perfect square, which I'm going to abbreviate P period S period. So if it's a perfect square, that tells me that, let's turn to the front. Remember, if it is a perfect square, that means it is solvable by factoring. Every quadratic is solvable using the quadratic formula. And technically you can complete the square for every quadratic. So for this one, because I got a discriminant that is a perfect square, that tells me this is part 1, or part A. The value of my discriminant is 1. Part B, the number of solutions we have. Since my discriminant is +1, that means it's greater than 0. So if I look on the front of the paper, if the discriminant is greater than 0, I have 2 real solutions. So we would say 2 real solutions. And then part C, what methods can you use to solve? Well, because it's a perfect square, we couldn't factor. Because every quadratic is solvable using the quadratic formula, we can use the quadratic formula. We could complete the square. However, because we have an x term as well as an x squared term, we cannot solve directly. So the only 3 methods we can use, remember we have a total of 4, is factor, quadratic formula, and complete the square. So number 6. Number 6, our a, b, and c. First of all, it is in the correct form, x squared x constant equal to 0. So a has a value of 2, b is -9, c is 15, and then we can plug that right in. So we have -9 squared minus 4 times a times c. So our discriminant has a value of, that would be 81 minus 8 times 15. So that would be 120. So if I do 81 minus 120, that is going to give me a negative discriminant of -39. So if my discriminant for part A has a value of -39, part B then means because it's negative, that would mean that the part that is under the square root in the quadratic formula is negative. So if I am trying to take the square root of a negative number. I'm going to end up with no real solutions, and instead of saying no real, we're just going to go right to saying 2 imaginary solutions. All right, part C then says what methods can you use? Since this was not a perfect square, it is not factorable, which means the only 2 methods we could use would be quadratic formula or complete the square. But because we don't know how to complete the square, the only option for us right now is quadratic formula. If you're really curious about how to complete the square, you can look that up on Khan Academy. They will go through it. It is a really useful method. It does take a little bit of persistence, but it's not bad. All right, so one of the things I want you to notice on this one is that this one is not set equal to 0. And remember, I need it equal to 0 with all of my terms on one side of the equal sign in order to use the quadratic formula. That includes finding just the discriminant. So because my lead coefficient is negative, rather than moving the other terms over to this side, I would move that over there. So I would add 4x squared. Then my new quadratic would be 4x squared plus 8x plus 4 equals 0. Yes, I realize I switched sides. The 0 would be on this side. It's still, the whole thing is going to be equal to 0, so it doesn't matter whether you write equal 0 on the left or on the right. All right, at that point, hopefully you see that all of these terms are divisible by 4. Do you have to notice that? No. Is it helpful if you notice that? Absolutely. So if I can divide everything through by 4, that means I can factor out a 4. And that actually, hopefully you can see that that is going to be factorable. But remember now at this point, I can divide by 4. Because I'm trying to solve anyway, it's totally fine to reduce it like this ahead of time to make your calculations easier. Now, I will say this, your discriminant will look different than people who don't reduce it. However, if it was a perfect square in this format, it will be a perfect square in the reduced format as well. If it's positive in the original, it'll be positive in the reduced, as long as you do the work correctly. So you don't have to worry about that changing the answer as long as you factor and divide out correctly. All right, so at that point we can identify our A, B, and C. So here we would have A equals 1, B equals 2, C equals 1. So when I use my discriminant, I would have B squared minus 4AC. So my discriminant would be 4 minus 4. Oops, sorry, C is 1. Don't write a C there. You need to put the number in. And that would be 0. If you remember from our table when we were listing our perfect square numbers, 0 is a perfect square. It is 0 times 0. So yes, that is a perfect square. So that means the original quadratic as well as the reduced quadratic are both factorable for solving. So that would be my part A is 0. Part B, we would have, be careful here, 0 is the only number that is neither positive nor negative. So if our discriminant is 0, it looks like I only have one real solution because that means that I'm taking the square root of 0, which is 0. And if I add 0 to the opposite of B, or I subtract 0 from the opposite of B, it's not going to change the value of what the opposite of B was. So I'm going to look like I have one answer because I'm not changing the opposite of B by adding or subtracting 0. And I'm still then dividing opposite of B by 2A. So remember, when that happens, that's why we have that multiplicity of 2. Also, because it was a perfect square, it was factorable. All right, let's go back. So what that means is we have one real, but there's a condition here. It has a multiplicity of 2. And I want you to write that down because every quadratic has two solutions. It's just whether or not it's the same solution, two imaginary solutions, or two distinct real solutions. All right, and then part C, since it is a perfect square, it's solvable by all four methods, which means we could factor, we could complete the square, we could use the quadratic formula. Oops, sorry, we cannot solve this directly because we have the x term, so I misspoke. We cannot use all four methods, we can only use these three. Okay? All right. I think you're getting the hang of it, so if you get it, you may stop watching the video. However, if you still need a couple more examples, I will go through these last four. I will do it a little bit more quickly, so you can always rewind and go back if you need me to repeat something. All right, so our quadratic is in proper form. The only thing we need to do is, because all of our terms are on one side, we need to set this equal to 0 so that we can identify then our a, b, and c. So if I say 0 equals x squared minus 4x minus 4, then I can see my a is 1, b is negative 4, c is negative 4. All right, so then our discriminant would have a value of negative 4 squared minus 4 times 1 times 4. A was 1, C was 4. So our discriminant would be 16 minus 16, which is 0. Oops. Sorry, C is negative 4. I went a little too fast myself. So if C is negative 4, that would be 16 minus negative 16. So minus a negative, remember that would be keep, change, change, which means 16 plus 16 is not 0, it's 32. 32 is not a perfect square. So while my answer to part A is 32, my answer to part B, it is still positive, so there are two real solutions. But because it's not a perfect square, we can't factor it. We can use the quadratic formula, or we could complete the square. We can't solve directly because it has an x squared and an x term as well as a constant. So if you have all three terms, you cannot solve directly. All right, number 9. Same idea. So this is essentially saying that this is equal to 0. If that's the case, then I have an a value of 1, b value of 8, and c of positive 4. Here C and B were both negative 4, and I was a little too quick on that one. All right, so the discriminant would be 8 squared minus 4 times A times C. So our discriminant would be 64 minus 16. That's 48. 48 is not a perfect square, so that means that it is not factorable. There's part A. Part B, it is positive. Since it's positive, that means I have two real solutions that are going to be different answers. And part C, because this is not a perfect square, it's not factorable, so my only two options here are quadratic formula and complete the square. All right, number 10. It's in the correct format, x squared x constant. So A is negative 1, B is positive 2, C is negative 4. That means when I plug that into my discriminant, 2 squared minus 4 times negative 1 times negative 4. So our discriminant is going to be 4 minus, that would be 16, which means that our discriminant is negative 12. That's part A. Because it's negative, it's not going to give us real solutions. Not only that, but because it's not a perfect square, there's no way it was factorable, in addition to the fact that it doesn't have real solutions, so it's not factorable over the real numbers. So we have two imaginary solutions. Since it's not factorable and I have all three terms, the only two options are quadratic formula or complete the square. All right, last one. Here we have a fraction. Remember, since to use the quadratic formula, we're saying that this is equal to 0. I can multiply through by the least common denominator like I've been recommending, especially on a problem like this, because I'm pretty sure you guys don't want to be plugging a fraction into the quadratic formula. You're going to want to make sure you give this a go and multiply through by the least common denominator, which would be 4. Whatever I do to one side, I have to do to the other to keep the equation actually equal. So that would give me 0 equals 4x squared plus 28x plus 1. Remember, we have to distribute that 4 to each term. And then from there, we can now identify our A, B, and C. So A is 4, B is 28, and C is 1. All right, so now our discriminant is going to be 28 squared minus 4 times 1. And I do not have 28 squared memorized. However, I know it's more than 729 because that's 27 squared. So our discriminant is 784 minus 16. 784 minus 16 is 768. And let me double check. I don't think it's a perfect square, but it's worth checking. It is not. So part A, my discriminant has a value of 768. Part B, it is positive, so it has two real solutions. And part C, because it's not a perfect square, the only two I can use because it has all three terms is quadratic formula or complete the square. The only way I would be able to say I could solve directly is if I were missing that x term and all I had was my quadratic and my constant. So that's what you're looking for if you're going to write that you can use that method. All right, guys, I hope this was helpful. That's all you have to do on the homework tonight. You do not need to finish the quadratic formula. You can if you want to, but you don't need to. All right? Thanks for tuning in, and I will see you on Monday.